Fundamentals of Software Architecture, Chapter 3, Modularity. So, this is going to be a pretty long one, but it's really interesting. It starts with a quote. 95% of the words about software architecture are spent on extolling the benefits of modularity, and that little, if anything, is said about how to achieve it, by Glenford J. Myers, and he said this in 1978. So bear that in mind. We're gonna end with an interesting thing. So modularity is a way of grouping related code together into modules. It is an organizing principle. To explain it using physics, software systems model complex systems, which naturally gravitate towards entropy or disorder, right? They get more complex, they break down, etc. In order to preserve order in the physical system, energy must be added. And same goes for the software. Architects must actively check and measure the quality of the software and architecture and do things in order to maintain good structural soundness, which doesn't happen by accident. We all know that. Modularity is not an architectural characteristic. Remember architectural characteristics from the previous chapters? Well, modularity is not one of them. There is no project that will have an explicit requirement to have a good modular distinction, right? But every project needs to maintain order and consistency. So it goes without saying, basically. Let's try to define modularity or modules. A module is defined as a set of standardized parts or independent units that can be used to construct a more complex structure. We describe a logical grouping of related code as modularity, and that can be a group of classes or functions, etc. You might think modularity is a developer's thing. Why would architects be concerned about it? Well, because the way that developers package the software, the things, the classes, and the modules can greatly affect the architecture. For example, reusability is much more difficult to achieve, if not like impossible, if multiple packages are tightly coupled together. When we're referring to modularity as grouping of code, we're not referring to physical separation, but a logical one, right? And when we're talking about multiple packages that are tightly coupled together, it doesn't mean that they're in the same folder or, you know, like a physical separation where they live, but a logical one, meaning do they call each other, do they depend on each other, and how they depend on each other. That's basically the modularity. So there are a few tools which are language agnostic metrics that we can use to measure modularity. And these are cohesion, coupling, and connascence. So this is a new word for me, and I believe for everyone, because even my computer underlined it with red, says like, what is connascence? But it actually is a term, and we'll check it out later. Let's start with cohesion. So cohesion refers to how related the parts of the code are to each other, right? A module is cohesive if all of its parts should be packaged together. If we break them into smaller pieces, it would require coupling the parts together with calls or imports between them in order to maintain the same functionality. There are multiple types of cohesion, and they're listed in this case from best to worsts. Okay, first we have functional cohesion. Every part, let me just do this, every part of the module is related to the other, and the module contains everything essential to function, right? This is like the best, the best type of cohesion, where we have one module, it doesn't have outside dependencies, everything it has, everything it needs, it has inside, it contains inside. So that is the functional cohesion. Then we have sequential cohesion, the relationship between two modules where one's output is the other one's input, right? That is the sequential cohesion. Think of these as like classes, functions, or, you know, if you're into JavaScript, like npm packages, and how they how they relate with your code base. Then we have communicational cohesion, when two modules operate on the same information or contribute to some output. For example, write something to the database and then generate a report based on that information, right? Then we have procedural cohesion, when two modules must execute code in a specific order. We're going to see something similar down below, but basically we have, I don't know, we have an email, sending an email example where we instantiate we instantiate the email class, and then we set the header or the sender, we set the body, and then we invoke the send method, and then we set the subject. It's too late, right? So yeah, that's procedural cohesion. Then we have temporal cohesion, when two modules must execute code at a specific time. For example, booting up your computer invokes a number of seemingly unrelated things, but all of them must be initialized when you start your computer. That is the temporal cohesion. Logical cohesion is the data within modules. The data within modules is related logically, but not functionally. For example, a module that converts information from text, serialized objects, or streams, right? And this is, for example, the string utils in Java, right? It's like a utility package that contains a whole bunch of utility methods that are seemingly, the operations are related because they're all on top of the string, but functionally they're very different. So that's logical cohesion. And at the end we have coincidental cohesion, when elements in the module are not related to each other other than them being in the same source file or the same file, right? This is the most negative form of cohesion, right? We have one file and it contains, I don't know, 3 functions, 2 classes, and they are not related to each other. That is the worst. Yeah, that's the coincidental cohesion. So one thing to note is that cohesion is a less precise metric than coupling, and it's often at the discretion of the architect. And here's an example. We have a class, customer maintenance. And this class has a bunch of methods like add customer, update customer, get customer, notify customer, and then we have get customer orders, cancel customer orders, right? This is the customer maintenance. So for the last 2, do we leave them inside of the customer maintenance class, or do we create a new class called order maintenance and keep them there? And of course, the answer, as always, is it depends. You gotta ask yourselves a few questions. Are those the only 2 operations that operate on orders? If so, I guess it's going to be fine if we leave them in the customer maintenance. If the orders operations grow, then it might make sense to separate them, right? Another question, is the customer maintenance class expected to grow? Do we anticipate more customer-related methods or not? That's also a huge factor. Would the order maintenance class require so much knowledge of the customer information? If so, separating them in 2 classes would require a high degree of coupling to make it functional. These questions represent trade-off analysis, and this is at the heart of the job of a software architect. I think in the previous 2 lessons or chapters, we've pretty much said the same. Trade-off analysis is at the very center of software architecture. You gotta see the pros and the cons of everything. There's a set of metrics named the Chidamber or Kidamber, I don't know how this is pronounced, but Chidamber and Kemmerer object-oriented metrics suite that includes many common code metrics. One of them is called the lack of cohesion in methods, or LCOM for short. This metric measures the structural cohesion of a module, typically a component. We have a math formula provided in the book. So LCOM 96 is the 1/a times the sum of m minus micro aj. I don't know. In other words, this is the formula if you want to if you want to look at it. But in other words, LCOM is the sum of sets of methods not shared via sharing fields. And here's also an illustration of the LCOM metric, and this is really going to clear things up, where the hexagons on the left side represent class fields, and the squares represent class methods. So class X on the left, we can see that we have A, B, and C fields or properties, and M1, M2, and M3 methods. We can see that the properties or the fields and methods pretty much use each other, right? M2 uses A and B, M1 uses B and C, etc. So we can say that the class X has a low LCOM score, and that indicates good structural cohesion, right? Y, on the other hand, lacks cohesion. For example, each of the field and method pairs can actually be refactored into its own class without affecting the other fields and methods. So this class lacks cohesion. Class Z, on the other hand, shows mixed cohesion. We can refactor the last two, C and M3, into its own class without affecting the AB and M1 and M2, right? So this is mixed cohesion. If you're refactoring, of course, this will help you make those decisions, right? That's what the LCOM metric is. It is very useful when moving from one architectural style to another. It can help you find classes that are incidentally coupled, just like we saw here. Have in mind that the LCOM metric does not have deficiencies. It can only find structural lack of cohesion, but it cannot determine logically if particular pieces fit together. And if you remember the second law of software architecture, why is of much more interest to software architects than how. So the LCOM metric, it can only find structural lack of cohesion. Okay, let's move on to coupling. In 1979, Edward Jordan and Larry Constantin published the Structured Design Fundamentals of a Discipline of Computer Program and Systems Design book, in which they defined the metrics afferent and efferent coupling. And these are, again, weird words, poor choice of words, but I think they come from mathematics. So, afferent coupling measures the number of incoming connections to a code artifact. For example, references that point to its components, classes, function, fields, methods, and so on. Right? These are the number of connections or the number of places where that code artifact, whatever it is being used, like incoming connections. Efferent is the outgoing connections. That's basically the dependencies of that code artifact, right? How many dependencies does it have? And to make it easier, you can come up with your own mnemonics in order to remember these better. For example, you can think of A in afferent as accepting or incoming connections, right? Or the E in efferent as exit or export outgoing connections. So that's coupling, basically. How many places depend on this particular, let's say a class, right? How many places in the code base depend on this class, and how many other functions or utilities or classes does this class depend on? That's basically afferent and efferent. Then we have abstractness, instability, and distance from the main sequence. And these are created by Robert Martin. And then these allow a deeper evaluation of the code base. For example, abstractness is the ratio of abstract artifacts. These are, by the way, on the whole code base. So the ratio of the abstract artifacts, like abstract classes, interfaces, type definitions, and so on, to concrete artifacts or implementation. A code base with too many abstractions is challenging to understand how things are wired together. Right? Everything is abstracted. And there's a formula to measure abstractness. It's basically the sum of the abstract artifacts divided by the sum of the concrete m to the power of c, concrete artifacts. This is abstractness. For example, an application that has 5,000 lines of code, all in one main method, right? So it has only one function, it has 5,000 lines of codes, all of them are in one method. The formula's numerator, or the top part of the formula, is 1, while the denominator is 5,000. So it's going to be 1 over 5,000, right? The abstractness of that application is almost 0, because it's not abstract at all, right? Then we have the instability metric. It's the ratio of the efferent coupling, or dependencies, right? E for exit or export, coupling to the sum of both efferent and afferent coupling. This is the formula. The efferent coupling divided by efferent plus afferent. And this is the instability metric. It determines the volatility of a code base. A code base with high degrees of instability breaks more easily when changed because of high coupling. If a class calls to many other classes to delegate work, it's more prone to breakage if one or more of the methods change, right? That means if we have like 5 outgoing, 5 external or outgoing connections, and not enough abstractions, like I don't know, 1 or 0, that's going to be closer to 1, 5 over 6. While if we have not abstractions, sorry, other dependencies on this class, where if it's the other way, if we don't depend too much on other classes, but other classes depend too much on us, changing the other classes is not going to, we don't need to change our class, right? Because it has more outgoing than it has more incoming connections or dependencies than it has other outgoing dependencies, if I explained that well. So that's the instability. And then we have the distance from the main sequence. This is a fun one. And this combines the abstractness and the instability metrics into one. It defines the ideal relationship between the level of abstractness and the level of instability. And of course, there's a math formula for that. Abstractness plus instability minus 1. There's a graph that will help us visualize. So this is the distance from the main sequence. If we chart instability and abstractness on a chart, draw a line between the ones, that's going to be the main sequence, right? And this is like the Goldilocks zone. And if we take our class, our method, our package, whatever we're working on, and we try to calculate the abstractness and instability and map them on this chart, we're going to get the point. The distance between the main sequence and this point is actually the distance from the main sequence, right? And you'll see what this means. This is basically exactly what I said. So there are 3 zones in this chart. The upper right zone is called the zone of uselessness. And this describes code that is too abstract and is difficult to use. The lower left corner is called the zone of pain. And it describes code that is with too much implementation and not enough abstraction. And this makes it brittle and hard to maintain, right? So in order to see where you fall or where your class falls, you need to do this exercise, chart it up, map everything onto this chart, and you'll see where that zone is. But basically, there is no plus or minus in this case. I mean, the book doesn't provide a specific range where this is. It's just a general rule of thumb. The closer you are to the main sequence, like this one, the Goldilocks zone, the better it is. Don't get further away. Okay. And lastly, we have Connascence, that weird word that I heard for the first time. So in 1996, Mailer Page Jones redefined the afferent and efferent metrics for object-oriented programming. And I forgot to mention that afferent and efferent metrics, they're for structural programming. We're talking about C and those structured languages. But in 1996, Paige Jones actually redefined this and for object-oriented programming through a concept he named Connascence. And Connascence is two components are connascent if a change in one would require the other to be modified in order to maintain the overall correctness of the system. Classic dependency, right? If A depends on B and B is in a way that if B changes, A needs to change, that means A and B are connascent, right? And there are two types of connascence, static and dynamic. The static connascence measures coupling on a source code level, in contrast to the dynamic connascence, which measures coupling during execution time. We're going to see that later. It's different. But yeah, he defined the following types of static connascence. We have connascence of name. Multiple components must agree on the name of an entity. Names of variables or methods are the most common way code bases are coupled, right? Based on the name. And it's also the most recommended because modern day tooling makes system-wide renaming trivial. You can just right-click on a variable if you're using VS Codes, rename the field or the class or whatever, and it's going to change the name in all of the other files where that thing is being used, right? And this is a code example of the connascence of name. We have a function, print full name. It takes in a user object and it prints the user's first name and the user's last name. The field names must match to what the function expects, right? We have the user object, the first name and the last name, and this is how we use them. By the name, right? We refer to these by the name, first name and last name. If this changes instead of last name to surname, this function is going to break because last name, that property does not actually exist. It has been changed to surname. So this is connascence of name, and this is the most recommended way of connascence. Again, we just want to rename this. We can rename this, and our IDEs are modern. They can figure it out where we actually use all of these objects, reference all of these objects. So of course it's going to be easy to refactor this piece of code. Then we have connascence of type. Multiple components must agree on the type of an entity. This refers to limiting variables and parameters to specific types. And bear in mind, this is not a universal language features. Like languages like Clojure, they have dynamic typings or selective typing. This is not going to apply in those cases, right? Check this out then. We have a function called calculate area. By the way, these code functions, I came up with them. These are not part of the book. I needed something to, explain these connascence types bit much, with code. Show me the code. Talk is cheap, right? Linus Torvalds. Yeah, so connascence of type. We have a calculate area function that takes in a shape. And it is similar to the connascence of name example, but in this case, we have a mathematical operation. We have width times the height. And in this case, we assume that the shape has numeric width and height, because we can't have width to be a number and height to be a string. Right? We cannot multiply numbers with strings, or height being something else, a Boolean, right? Yeah, these two must be a number. So imagine this is someplace else, right? In a different package of ours, and we import this and we use this in a different package, then these parts, these two must be numbers. This is the connascence of type, right? Then we have connascence of meaning or connascence of convention. Multiple components must agree on the meaning of particular values. The most obvious case is hard-coded numbers rather than constants. For example, we have a function called isAdmin. We take in a user and we check if the role is equals to 1. And we assume that 1 means admin, right? Then we have the user with the role set to 1. It's not explicitly documented. It's not self-explanatory. right? We don't know the meaning of role of one, hence the connascence of meaning. We don't know the meaning directly. It's not documented. It works, right? But if we change the meaning of one, then we need to update the this function as well. If the admin changes to 0 or 2, if we wanted to, create a super admin and the super admin is going to be 1, but just the regular admin is going to be 2, we need to update everything. And if we do this, especially this way, even our IDEs won't be able to help us. I mean, it's tricky to find where the role is being compared to a specific number. It's going to have to be like a global search of strings, but not references. And sometimes you might have 2 instead of 3 equal signs. So yeah, good luck with that. And sometimes you might even define this above and not like as like a global constant. So yeah, that is the connascence of meaning. We should, in this case, we should just use constants. Define it someplace in the constants.ts or config or whatever, or as like an environment variable, and use that one instead of a magic number or a magic value like this one. Then we have the connascence of position. Multiple components must agree on the order of values. And this refers to the ordering of arguments. If there's a function update seat where it takes a name as a string and a seat location as a string, and the developer calls it with update seat 30G and Lazar Nikolov, it's the types are correct, but the semantics are not correct. We put the name as the second argument, right? But the second argument is a seat location. So our IDE is not going to complain. This is going to be just fine, right? Both are strings, but it's on your responsibility to make sure that the orders or the positions are correct. Again, just as we mentioned, update seat, name and a location. Name has been assigned to seat location. If we update the seat with Lazar and 30G, the output is going to be Alice. I didn't change this one. Alice has been assigned to seat 12A. If we swap the seat number and the name, it's going to say 12A has been assigned to seat Alice, or 30G has been assigned to seat Lazar, which is incorrect and it's nonsensical. Lastly, for the static connascence, we have the connascence of algorithm. Multiple components must agree on a particular algorithm, and a common case is encoding and decoding data. Both the encoding and decoding processes or functions must adhere to the same algorithm in order to maintain correctness, right? For example, we have an encoding function where we reverse and encodes a string to base 64. And the decoding function must do the same, but reversed, right? Reverse the base 64 and decode it again in order to get the original value back. And if the encoding changes, if we don't do the reverse, or if we change it, from base 64 to something else, then the decoding function must also change. So these two functions are connascent to each other based on the connascence of algorithm, right? There we go. If we have book club, if we encode book club using this function, we were going to get this base 64 string. And if we pass that encoded string, we're going to get back book club. It's going to be the same. All right, then we have, aside from the static connascence, we have dynamic connascence. Again, with this analyzes calls at runtime, and there are 4 types for it. There's a connascence of execution. The order of execution of multiple components is important. And this is that email example that I mentioned earlier. We instantiate a new email, we set the recipient, we set the sender, we send the email, and then we set the subject. It's too late now because the email has already been sent, right? We can't set the subject after sending the actual email. So yeah, connascence of execution is the order of execution. Someone asks, could the connascence of position be solved using a declarative object parameter function, like function name and seat location? This way we can prevent mistakes. True. In this case, the top level or like the actual argument is just one, right? It is the object containing the name and the seat. And there is no positioning in this case because it's just one object. And yeah, this is how we can solve the connascence of position. One way. Some languages also support named argument. For example, like Python. In Python, you can literally say, open Western. For example, in Python, you can literally say, I don't know, assign seat. Let's use that one. Name equals Lazar, and seat location equals I don't know, 14a. Even if we change seat location to be the first argument, it's going to be okay because these are named. So the connascence of position is not applicable in this case if we used named arguments. Yeah, connascence of execution. The order must be the order is important, and the components in this case are also these methods. Right, these are on the same class, but these are still maybe not relevant to each other. There's like a connascence of wasn't a connascence actually. They were, let me see. There's a cohesion. Yeah, they have communicational cohesion, right? They operate on the same information or contribute to the same output, right? We have an email. Let's go back. We have an email, and these methods have that communicational cohesion. They contribute to the same object, which is the email, right? And then we send it. Right, then we have connascence of timing. The timing of the execution of multiple components is important. The most common case is race condition caused by two threads executing at the same time, affecting the outcome of the joint operation. Here's a code example that I've seen way too many times in my life. We have a file processing function. We read the file, right? And we assign the data to the file contents. But then we say console.log file contents to uppercase, right? If this is not synchronous, if this is asynchronous, this is going to get executed in a different, it's not going to be a thread in JavaScript, but imagine it as a thread, right? The console log will happen immediately. It's not going to wait for the file to be read and the file contents to be assigned. The values, it's going to just console log something to uppercase. This is not initialized, so it's going to break. It's going to say to uppercase of undefined. There's your error. So connascence of timing. Then we have connascence of values. Occurs when several values relate to one another and must change together. For example, a rectangle with 4 points. We can't really change one point without considering the impact to the other values, right? If we have 4 points, we have a rectangle. If we change the rectangle's top right point to be somewhere below the bottom right, it might not even be a rectangle anymore. It's definitely not going to be a rectangle, right? So that is the connascence of values. The other points depend, like points depend on each other. And here's a different example. Again, a read config function that points to a configuration path. It's hard-coded, right? We decided that this is going to be the path where we keep the configuration. We read the file, we parse the JSON, and we console log the config, right? And then someplace else, we have an update config function that gets the new configuration, right? We read or assign the config path again to the same value, hard-coded, and we write whatever's, you know, in the new config there, and we'll say config updated, and we can just update the config. In this case, if we change the config.json location, we have to change it in both places. And this is the connascence of values, right? These two functions are connascent to each other because they try to access the same resource through this config path value, and therefore it must be the same. Again, this can be a constant defined somewhere. All right, then we have connascence of identity. And this occurs when multiple components must reference the same entity. We have, in the main application, we have an object user with the ID of 123. And we log out the user, great. But then in a different analytics service, which is like in a different part of the application, maybe even like a different application, right? If this is like a microservice application, it might even be a different project. We are accessing, we have like a log user event that logs the user event for that user, and we log the user event with 123 as the ID. We basically assume that 123 is Alice, right? And this is connascence of identity. These two components, the main application and the analytics service, must reference the same entity. If we're talking about Alice with the email alice@example.com, then these two must be talking about the same Alice, right? That's the connascence of identity. This is not something that we encounter in modern day times. We have databases, we have IDs, but sometimes if we like hard code or type stuff, if we're not talking about a database with a self-assigning identifier, we could run into this. So yeah, that is connascence of identity. And each of these connascences, is that the plural form? Each of these connascences have their own properties, like strength, locality, and degree. Strength defines how easy it is to refactor that type of coupling. Some types of connascence are easier to refactor than others. I mentioned this, right? We had the name and type. Let's take the name, for example. If I want to change the name of the property or the field in that place, I can just rename it, and the IDE itself is going to find all the references and change the name there. Easy refactor. It's literally just one single execution on the IDE. And the architects and developers can improve the coupling characteristics of their code base by refactoring towards the better types of connascence. Static is preferred over dynamic because it can be determined by a simple code analysis, right? Our IDEs can do this for us. And modern day tooling makes it easier to improve static connascence. Again, for example, a case of connascence of meaning, this one, and that was is admin if the role is equal to 1, can be improved by refactoring it to connascence of name just by creating a named constant rather than using a magic value. Instead of having or assuming that role equals to 1 is admin, we're going to create a constant admin role ID, assign that to 1, and then we can use that in both places, right? So we're refactoring from connascence of meaning, we're refactoring to connascence of name. That's it. So these are all the connascence based on their strength, right? And we should prefer to refactor towards this way, right? If we have position algorithm, we should try to refactor that way as much as we can, right? Algorithm might not always be like the case. If we're base 64, if we implement base 64, then we implement base 64. We can't really replace that with a name or something like that. But yeah, when we're refactoring, we should strive towards refactoring that way, in that direction. Cool. Locality measures how proximal the modules are to each other in the code base. This is like a physical organization. Proximal code has more and higher forms of connascence than more separated codes. For example, if two classes in the same package have connascence of meaning, it is less damaging to the code base than if two different packages have the same form of connascence or the connascence of meaning. Why? Because within the package, we can have a connascence of meaning if we can't refactor it towards a type or name. We can have connascence of meaning I mean, yeah, ideally we shouldn't have, but if we do, it's going to be less damaging than having two different packages having the same connascence of meaning, right? Because that can mean different things in these two packages. And if we don't refactor it with a more precise one or a more accurate one, like type or name, that's going to cause more damage, than just like that's locality, localizing the connascence of meaning within one package or even within one class. All right. Then we have the degree property, and this relates to the size of impact. Does it impact a few classes or many classes? The smaller the degree is, the smaller the damage is. Page Jones created 3 guidelines of using connascence to improve our system's modularity. First, minimize overall connascence by breaking the system into encapsulated elements. The second one is minimize any remaining connascence that crosses encapsulation boundaries. And third, maximize the connascence within encapsulation boundaries, right? These are basically refactoring guidelines. Minimize overall connascence by breaking the system into encapsulated elements, meaning don't have one class, don't have a God class. You've probably heard of the term God class, which refers to a class that does way too many things, right? And you can even use the the LCOM, to see if you have a God class or not, or if you can have, multiple and break it down into like smaller elements, smaller classes. That's what the first one refers to, the first guideline. Yeah, minimize overall connascence by breaking the system into encapsulated elements, right? Minimize any remaining connascence that crosses encapsulation boundaries. This is that thing, right? If we have multiple classes, but they have to be connascent, they're doing the same thing or a relevant thing, then we better, refactor towards this way so that it's easier to refactor, or it's less damaging to the code base. And then maximize the connascence within encapsulation boundaries. That means within the individual classes that we refactored, right? We had one God class, we refactored into multiple smaller classes. Within those classes, we need to maximize the connascence, just like class X, right? And keep breaking it down until we reach like a really good class X type of class, where the LCOM score is low, basically. That indicates good structural. Let's see, in connascence of meaning, when we created a name constant to store this magic number, it sometimes increases the amount of boilerplate in our code. I understand this is the correct approach, but is it sustainable? It is. It's better to have, it's better to have boilerplate code. It's less damaging to have boilerplate code that you can easily update and change than, having a magic number that's like even hard to find. Even search within the project might be hard. It's not going to uncover all of the magic number instances because one is just one, right? So again, we're talking about trade-off analysis in this case as well, right? There's pros and cons. You get a reference and like a LSP reference with the constant, but you also get boilerplate. If I were to pick between one of these, it would have been the left one. I would pick it. I would take boilerplate because it's going to be easier to update later on. Yeah. Okay, so Jim Weyrich, that's the Rake guy. I think he's like a legendary architect. Ruby on Rails, not on Rails, but just Ruby in general. He repopularized the concept and offers 2 pieces of advice. Rule of degree. Convert strong forms of connascence into weaker forms of connascence. And also rule of locality. As the distance between software elements increases, use weaker forms of connascence. That's this, basically, based on the strength, right? Yeah. And of course, we should talk about the problems of the Connascence defined in 1990s, because this is already at some degree outdated. There are multiple problems. First, these measures look at lower levels of code and focus on quality and hygiene rather than architectural structure. Architects should be concerned of how modules are coupled instead of the degree of coupling. As you notice, we talked about really low-level code stuff, how we implement things, how we refactor things into like multiple classes and stuff, right? That's not necessarily of concern to the architects at that degree or at that level, right? So yeah, architects should be concerned of how modules are coupled instead of, actual implementation details. And second, it doesn't really address the fundamental decisions that many modern architects must make. For example, like, should we use synchronous or asynchronous communication in distributed architectures like microservices? Coupling in Connascence and stuff like that, it's not going to help you make that decision, right? But in chapter 7, we're going to see new ways to think about modern Connascence. It's updated. I haven't read chapter 7 yet, so we'll see. We'll see what are the new ways to think about modern Connascence. But yeah, this was chapter 3, modularity. You can find the source code on my GitHub repo, Fundamentals of Software Architecture, on my account. And yeah, the next chapter is the architecture characteristics defined. We're going to talk about the ilities, scalability, and what else was there? Security is not an ility, but yeah, security, elasticity, testability, and stuff like that. So yeah, that's going to happen next